we can further study interesting phenomena and start to move on to what happens in a simple harmonic oscillator. So what I'm going to do now is I'm going to take my initial wave packet, so my wave function psi squared, which of course is giving me the probability is what we're actually looking at, right? So I will still have my wave packet, and it's going to be, sitting here sort of in the middle of that screen there. But what I'm going to do for my potential now, V of x, is going to be a harmonic oscillator potential, right? So we know that initially what we expect to happen is that my particle should spread, but now when I put this harmonic potential, my particle is actually connected to a spring. So initially it's going to spread, but then the question is, what will this potential do as the particle tries to spread and stretches out that spring? So that will be our next movie. So here we go. Ha! You see? So again, I'll back it up for you. So I start with my initial packet. It then, you'll notice, is spreading out like it normally does. But then what happens when it spreads too far, the spring begins to pull back on the particle, and actually it rebounds back, and then it just continues oscillating like this. And one of the neatest things is it's going to oscillate with exactly the frequency of the harmonic oscillator. So that's a kind of a very neat and interesting result. Now, we can ask, well, wait a minute now. The particle actually was able to spread out before the spring was able to pull it back. So my next movie, what I want to do is I want to take exactly the same thing again, right? But I'm going to increase the spring constant. So I'm increasing the spring constant K. And if I tighten up that spring constant, that will be my next movie. Again, you'll see I'm going to start at my usual Gaussian packet. But now when the spring is tighter, here's what we see. So we'll back up and see what's happening. You'll notice it's growing taller now. So I start here, but with a tight spring, the packet itself is already spread too wide. And the spring then, as you can see, it's grabbing it, and it's actually pulling that packet in so that it peaks up too high now. And then it continues along with its oscillations that again occur just at the frequency of the harmonic oscillator. Now, between these two, that should get you wondering, is there sort of an in-between case, right? You could call this the Goldilocks, because it's just right. The Goldilocks simple harmonic oscillator. If I find the perfect spring constant, K, to match my Gaussian, can I find a spring constant in between that just balances between letting it spread out first or pulling it in too tightly? And here's what we can get if we do that. Ready? That movie's actually playing. If you look very closely, you can see maybe tiny changes because of my numerical solution. But what you'll notice is this thing is pretty rock solid. It is not moving at all. And that's a very important type of quantum state. There's a whole class of these. These are called stationary states because their probabilities don't evolve in time. And we will learn later that actually stationary states are the same thing as pure states of the Hamiltonian or pure energy states. And as you know, as we had seen previously when we had done the Bohr-Sommerfeld quantization, there's a whole series of states for the harmonic oscillator, right? It's not just one state like this. There should be a whole series of pure energy states, and therefore, correspondingly, a whole series of stationary states. And in fact, we can take a look at some other states that I can show you here are indeed stationary. Here's one. This is actually the n equals 1 state of the harmonic oscillator. So this is SHO n equals 1. Let me play that again. I see we lost the movie. But if when I play it, again, perfectly stationary, you'll notice it's interesting. The probability actually goes to 0 at a certain point right in the middle. That's kind of the main difference. It took this original peak that we had and sort of split it into two with a point that has exactly 0 probability. And we can actually find other ones. Here is the fifth quantum state. So that's number 9 is SHO, simple harmonic oscillator, n equals 5. Again, it's perfectly stationary. It's an interesting shape. As you can see, it's now got 5 places, 4, I guess. 1, 2, 3, 4, no, 5. 1, 2, 3, 4, 5 places where it has hit exactly 0. And it's doing this other interesting thing, which is the probability seems to be getting higher near the edges. And there's a very good reason why that happens, and we will study that later when we learn about the harmonic oscillator. Now, if we continue on to our next movie, we can do something else where now we're going to explore what happens when I displace my wave function. So I'll have the simple harmonic oscillator. I'm still going to have, of course, my potential, which is nice and parabolic. But now I'm going to start off my wave packet off-center. And this also does something very interesting that we can study. When we do that, so I'm going to pull it off center, but it has just the width which likes to stay stationary. When I do that, I get this. It keeps exactly its same shape. It's really beautiful, but it's just oscillating back and forth, packet behaving just like you would expect a classical particle to behave in the harmonic oscillator. It just has a certain uncertainty associated with its position. And then finally, what we can do is we can take a simple harmonic oscillator and a random wave function. I just made up some random shape. It's interesting to see what this will do. When we look at that, what you will notice it does is the following. Oh, that's not the next movie. Here's our next movie, right? So it's some kind of crazy shape, right? Who knows what it's doing? But you'll notice it oscillates back and forth perfectly repeatedly. So when I have that behavior, I get strange behaviors, but it's still perfectly periodic in time. And the periodicity that it has of time t, the classical period of the orbit. So this gives us some then good intuition for the various behaviors that we can expect of the harmonic oscillator before we then go on to begin to consider things a bit more formally.